Let's talk about Laplace transforms. They're named after the French mathematician Pierre-Simon Laplace. Let's say we want to solve the initial value problem, dy dt equals y minus 4 e to the negative t, y of 0 equals 1. We've seen different techniques we can use to solve this. Here's another way to solve such problems. Use Laplace transforms. Given a function y of t, the Laplace transform of y of t is defined. L of y of t, we use that script curly L there, equals the integral from 0 to infinity of y of t e to the negative st dt. Or in other words, capital Y of s. That's often the name we give to this function. For all s in which capital Y of s is defined. So for example, find the Laplace transform of e to the t plus 7. Laplace transform of y of t is defined in this way. We saw that in the previous slide. So now just replace y of t with e to the t plus 7. Okay, we have the integral from 0 to infinity e to the t plus 7, e to the negative st dt. And let's combine these exponents. You learned those exponent rules years ago. Integral from 0 to infinity e to the t plus 7 minus st dt. We've seen before that we can factor out the t. So we have e to the 1 minus s times t plus 7. And then when we integrate that from 0 to infinity, now I know we learned in calculus 2 that we should replace the upper limit of integration with a b and let b approach infinity, but I'm just going to gloss past that detail because you know how that works. You've seen that before. So when we integrate, this is what we get. E to the 1 minus s times t plus 7 over 1 minus s. And plug in t equals infinity, plug in t equals 0, or really let the limit of integration approach infinity. As it approaches infinity, this expression just goes to 0. Okay, that's what happens as t approaches infinity. Plug in t equals 0, and we get this. That simplifies to negative e to the 7th over 1 minus s. In other words, e to the 7th over s minus 1. So that's our answer. That's the Laplace transform e to the 7th over s minus 1. Now, this is not defined for all values of s. It wouldn't make any sense for s equals 1. Usually, we want the values of s to be from some point onward to infinity. So in this case, it would be 1 to infinity. So this is defined for s greater than 1. Now, you may be thinking, holy cow, that was a lot to do for just one stinking Laplace transform. It was, but we have tables of Laplace transforms, so we're not going to have to go through all that rigmarole every time we evaluate a Laplace transform. For example, find the Laplace transform of each side of the differential equation dy dt equals y minus 4 e to the negative t, y of 0 equals 1. Our first step is to take the Laplace transform of both sides. So this is what we get. To evaluate the left side, use these formulas. Okay, so these are Laplace transforms for derivatives. L of y of t is just capital Y of s by definition. We saw that earlier. L of y prime is s, capital Y of s, minus y of 0. Y of 0 in this case, that's the initial value. And Ly double prime equals s squared, capital Y of s, minus s, y of 0. That again is the initial value, minus y prime of 0, another initial value. So the left side, L of dy dt, in other words, L of y prime of t, is just going to be s, y of s minus y of 0. So that's the left side of this equation. To evaluate the right side of the equation, use these formulas. Mercifully, the Laplace transform of the sum is just the sum of the Laplace transforms, and the Laplace transform of kf equals k times the Laplace transform of f. That's where k is a constant. And these rules are true because basically the Laplace transform is an integral. And you can break up integrals, and you can also pull out constants to the outside. Okay, so again, the right side looks like this. And we can break that up as L of y plus L of negative 4 e to the negative t. In other words, it's L of y minus 4 L of e to the negative t. So we know how to calculate, L of y. L of y is simply y of s. We've seen that before. And there are tables that we can use to evaluate this and this. Okay, we've seen these before, Laplace transforms for y, y prime, y double prime. That's great. L of 1 is 1 over s. L of t to the n factorial over s to the n plus 1, where n is a positive integer. Here's the formula for L of the square root of t. L of e to the at, that's the one we're going to use. It's 1 over s minus a. That'll come in handy in a moment. L of t to the n, e to the at, another formula we can use. This is where n is a positive integer. Laplace transform of sine kt, cosine kt, sinh kt, cosh kt. Remember that sinh and cosh are hyperbolic trig functions. We learned those in second semester calculus. And we also have Laplace transform of e to the at sine bt, e to the at cosine bt, etc. There are numerous formulas I could give you, but if you need more, they're just available online. You can find them there. Okay. So we've seen what the left side is. This is sy of s minus y of 0. Laplace transform of y is simply y of s. And as for this one, the Laplace transform of e to the negative t is 1 over s plus 1, because the Laplace transform of e to the at is 1 over s minus a, and we're just plugging in a equals negative 1. Now in a later video, we'll look at inverse Laplace transforms and see how to solve this initial value problem. Because right now, I've just taken the Laplace transform from both sides and I haven't done anything with it. We'll see later what to do with it. Here are some other ways we can evaluate Laplace transforms. Suppose we want to find the Laplace transform of t plus 5 squared. Well, we would just multiply that out using FOIL or however. That's going to be L of t squared plus L of 10t plus L of 25. In other words, it's L of t squared plus 10 L of t plus 25 L of 1. We've seen based on the previous slide that this is 2 over s cubed, 2 factorial, which is 2 over s cubed, 10 over s squared, and 25 over s. And again, this is going to be defined from all s. From some point onward here, s would have to be 0 onward, so s is greater than 0. How about the Laplace transform of sine squared 3t? For this, we use those formulas that we learned in pre-calculus or in calculus 2. Sine squared alpha is 1 minus cosine 2 alpha over 2. Cosine squared alpha is 1 plus cosine 2 alpha over 2. So the Laplace transform of sine squared 3t is, again, so what we would do is just plug in 3t for alpha, and we end up with sine squared 3t equals 1 minus cosine 6t all over 2. Let's break up the right side. That's L of a half minus L of 1/2 cosine 6t. That's 1 over 2s minus 1/2 s over s squared plus 36. Now, this is going to be defined for all values of s. No problem there. This is going to be defined for s greater than 0.